Good morning, everyone. I hope you all made it out of the long registration queue okay. And thank you very much to the organisers for putting on a fantastic workshop. I'm very much enjoyed the first talk and the introduction and looking forward to the rest of today. So with my brief time with you today, what I'd like to do is cover at a very high level. In a short period of time, you don't get to go into much detail, which is fine. What I want to do is touch on two key, capabilities or challenges that we've been attacking in the area of construction, but also related areas like mining. Watching the last, I was thinking there should be a prize at the end of the day for the company, the machinery OEM company that appears most frequently. I think after my talk, Caterpillar will be winning, but we'll have to see at the end of the day who has the most name drops in slides. And then I'll conclude the talk with a little bit of content to the debate and the panel Q&A. We got stuck into the debate early at drinks last night, and so we're already very warmed up. Very briefly, I come from a large robotics center at QT. I'm joint director there. We have over 100 researchers doing fundamental research and applied research in a large range of domains. And a lot of what I'll say today is drawn as just as much from inspiration and insights from other domains apart from just construction robotics. My personal group does a lot of work on positioning, technology, mapping, SLAM, which is obviously always a popular topic at conferences. And for the next 5 years, we're leading a wide portfolio of research into positioning and mapping research, including in areas with industry, perhaps construction as well. So some of the applied areas we work in that will be relevant to this talk include areas like mining, and we've touched on construction as well. And so a lot of the insights at the end of the talk will come from not just construction, but also some other fields which arguably are further progressed in automation than construction is currently. So the first challenge I'll touch on, and I'm not going to give you any satisfying detail whatsoever because you can't do that adequately in a short presentation, but really this whole issue of perception. And we saw that in the previous talk. And so one of the particular areas we've worked on is hazard detection on construction sites and also on mining sites and on roads, but we also applied it in the construction site area. And really the fascinating perception challenge, especially if you're interested in computer vision in this area, is simply that you can't just run an object recognition pipeline on a construction site. And so this is a very cliched example, but it illustrates the point perfectly. If you have a ladder standing up against a wall, it is not very much of a trip hazard for a human worker in that environment. But if you lie that ladder down on the ground, it becomes much more of a relevant trip hazard. And so if you just run an object recognition pipeline, you're not going to pick up that subtle distinction. So you really need to look at things like affordances of the object in the context in which you find it. And construction sites, if you've ever walked around one, especially a commercial building construction site, are the most fascinating, ever-changing, full of corner cases examples that you can ever come across in terms of seeing and understanding environment. And so we did some work, this was a couple of years back now, on seeing if we could train the then state-of-the-art pipelines using a combination of early, mid, and late fusion techniques to just from, visually labeled data, learn how to recognize the affordances of these trip hazards in the context in which they're found. And so we did this on a number of commercial construction sites, over sort of multiple floors of a largest construction site, and experimented with a range of different pre-processing techniques. One of the most interesting ones we worked with was HHA, which basically transforms your depth image into a sort of ground relative 3-element encoding of the scene. And we ran this number of systems, and we were able to show, and this is published in ICRA, that you can detect in the context in which it's found the trip hazard affordance of a number of objects in construction sites. And of course, construction relates to other domains, so we also ran this in other domains like mine sites as well. And once again, you're able to find the trip hazard affordance or danger affordance of a number of objects. The most challenging thing we found, and maybe construction sites don't have this as often, was drop-off hazards. So if your vehicle is in danger of driving off the edge of a cliff, it's very hard to visually recognize that, which was an interesting insight from that work. The second key challenge I'll touch on, which is universal to all of robotics, but I think particularly so in construction robotics, is the challenge of knowing where you are. And that's a nuanced, multifaceted problem. It's not just a GPS fix. And so we know there are many high performance positioning systems. Tomorrow at the VPR challenge, I'll talk about how none of these systems really work that well out of the box once you put them in challenging real world conditions, including our own positioning systems. So I'm not picking anyone else, picking on anyone particularly. But in construction, the key questions are what capabilities does positioning? And I don't just mean GPS positioning unlock. What's the exact functionality you need from your positioning system, and are current state-of-the-art systems really fit for purpose? And particularly, what are the best metrics by which to evaluate this functionality? So we're at a research conference. We're interested in metrics and performance evaluation that can act as a proxy for whether this system's actually going to work in the real world. And I would argue that most of the metrics that you'll find in papers, including our own papers, just once again, I'm not picking on anyone, are completely not fit for purpose for evaluating the translatability of this work into the real world. So positioning types, absolute positioning, like an absolute global positioning fixed from GPS. Relative positioning, very relevant for another sub-range of tasks that you might want to do on a construction site. Obvious things that positioning unlocks on a construction site are navigation from A to B, whether it's for a person or a drone or a robot. Relative positioning for things like drilling and sort of fine positioning tasks. Positional information to humans, autonomous workers, perhaps an inventory management system, so you can localize all your inventory on your construction site. And it's a foundational part of a lot of other foundational capabilities like mapping, surveillance, and so forth. Safety monitoring as well, potentially. And so one of the areas we've done a lot of work, which is related to construction, is in the mining domain. And you'll see constantly mining and construction work mixed because there is such strong interplay between these two. So unlike construction, I think you would say mining has had widespread commercial usage of autonomous vehicles for a long time now. It's one of the flagship examples of robotics actually making a commercial difference. And so we did some work with Caterpillar and a number of other partners on improving the positioning and mapping and navigation capabilities of their autonomous underground local dump truck fleet. So the previous speaker was mentioning that compared to a sunny day on a Californian road or Philadelphian road, these underground environments can be very challenging. This is an underground environment that these vehicles autonomously navigate through under good conditions, but it can get much worse. So you can have rocks hit your sensors, you can have dust, you can have water on the lens, you have glare in an otherwise nearly pitch black environment. So it's a very perceptually challenging environment. And you would see analogous problems to this on a lot of construction sites as well. And so we've done a lot of work on, we didn't try and de-noise the images, we just tried to learn how to throw out the images that were too noisy, but obviously if all of your images are too noisy, that doesn't work very well. And some of the kit that you see, and you'll see these on some of the experimental autonomous vehicles in construction as well, you have toughened, hardened camera sensors, and this is what the sensor rig looks like before it goes out on site, and this is what it looks like after only a couple of days operating on site. So you get dust, all sorts of dirt on it and everything else. So it's very perceptually challenging. People have even talked about putting windscreen wipers on your cameras to keep them clean, which is a nice idea. And this is the sort of size of some of the machinery that you're dealing with. And these companies tend to work both in mining and construction. The construction vehicles are often smaller, but they like using the same autonomy stack where possible across both of these different areas. And this is relevant to the debate later. Usually to go to fully autonomous systems, you add 1 or 2 zeros to the price of the R&D. And in a lot of situations, it's much more practical to develop a highly autonomous semi-supervised approach. So we developed semi-supervised SLAM solutions because it fit into the practical workflow of the construction or mining site. Other things that are interesting is not all errors. So whether you're doing object recognition or positioning, not all errors are created equal. And so for an autonomous vehicle in a mining context, the lateral error of where the vehicle is relative to the walls of the tunnel, or you can imagine the walls of the building site, is much more important to get right than the longitudinal error, which is the error up and down the tunnel until you get close to a junction point. And that's for obvious reasons. You don't want your vehicle bouncing off the walls, but if you're a few centimeters off longitudinally, it doesn't necessarily matter except at a critical junction point. And you can think about how you'd reevaluate the positioning requirements of your various autonomous vehicles and drones in a construction site context. And not all sensors have equal errors. So once again, lasers, cameras, we use all of them, LiDAR. The error distributions that these systems give you out of the box relative to the local environment and the local geometry are not the same for different sensors. So they complement each other very well, and that's why you see multi-sensor rigs. So this is a system in operation. This is a positioning and navigation system doing a, I think, 5 to 10 kilometer journey, 600 meters underneath the ground, localizing in one of these mine sites. We've done trials across, I think, 4 different sets of mine sites in Australia with Caterpillar, who's now taking this work on board. There are less obvious capabilities that positioning would give you on a mine site. You can learn place-specific higher-level functionalities, and I see Maurice in the audience, but Oxford University has obviously led a lot of this work where you learn task-specific behaviour at specific places in your environment. You can imagine that being very relevant to the construction site. You can also boost the performance of your higher-level systems like object recognition, depth understanding, and so forth by doing it in a place-specific basis as opposed to applying a generic system. And semantic positioning is sometimes more important than geographic positioning. So understanding that you're in a certain type of place rather than in a specific unique location in the world is once again sometimes more useful. So an example of how you can boost high-level task performance is semantic mapping. So from some colleagues in our group, you basically learn different parts of an environment, and you can imagine doing this on a construction site, and then you can massively boost the results of higher-level functionalities like an object recognition pipeline, for example, by doing it in a place-specific context based on priors that you've learnt about the characteristics of that place and what tends to appear. So what functionality is needed? So I ranted a little bit before. The research community is understandably a little obsessed with accuracy, precision, and recall, and they dominate research. And it's very hard to get your papers accepted without doing well at these metrics. But there's a lot of other metrics that are particularly important, especially in safety critical applications you could imagine happening in construction. So knowing when you don't know is very important. And worst case performance is much more important usually than best case performance if you're actually deploying a system in the world. And this comes into things, and this could be for your object recognition pipeline, whatever task you're doing, things like concepts of integrity, trust, auditability, provability, and guaranteed performance bounds are all massively under-investigated areas in the research field that will help us translate these systems into construction. Knowing when you don't know, a simple example of this, imagine you're making safety critical decisions based on an understanding of where you are on your construction site. If you have a system that's accurate 99.9% of the time, but lacks any ability to introspect, that is arguably not as good as a system that's accurate 99% of the time, but in the remaining 1% of time, so to confuse with numbers, 99% of that remaining time, it knows it's not performing well. That's very relevant to the debate later because you can hand over control. You can reach out, the robot can reach out and go, hey, I need help, and hand over control to that remote operator. But it has to know that it's in trouble. And that's something most systems are not very good at this stage. And worst case coverage is also another concept here. So we don't really care about best case positioning performance in a lot of applications. We care about when it's performing at its worst, because that's when you're going to see potentially dangerous or catastrophic things go wrong. So new metrics, I would argue, are critical to investigating, I guess, how we balance full automation with semi-supervised or teleoperated semi-supervised automation, especially in the construction field. Not so feasible in mining or some other areas like space robotics because you have issues like latency, but in construction site, there's no reason that this wouldn't be feasible. So just to conclude, I guess, I always like in my other, the other sectors we work in to sort of touch on some big picture reasons. So you always need to ask why are you trying to automate, and the introductory talk covered a lot of these: economic reasons, safety, throughput, performance. Performance benefits of automation can be multifaceted. It could be better at what humans already do. It could do more of what humans already do, working 24/7, or it can do something that humans couldn't do at all, opening up radical new paradigms and radical new capabilities in the construction area. You should also ask why not, and this is once again playing to the debate that will happen. Obviously, people are concerned about job reductions. The argument countering that is usually that it creates new, more interesting jobs. You have to be a little bit careful though, because if you just let humans fill in the capability gaps of the automation, you do not necessarily guarantee that those jobs that humans are doing are fulfilling or rewarding jobs. And so it's something you have to be very careful. And the other thing about jobs is a company locally can argue that if they adopt automation, they stay competitive and they actually maybe grow because they're competitive. but you have to look at the sector as well. So even though 1 or 2 companies are doing very well, the whole sector's employment population may shrink. So there's subtle nuances here that need to be discussed. So what's going to happen in the future? It's interesting to compare the scale of transformation needed for highly autonomous construction sites versus these other fields. So robotic process automation, by definition, is set up to slot into existing workflows and not need any changes to those workflows. And then you have logistics warehouses where they've built the entire warehouse to suit automation. You've got autonomous vehicles, you've got the fully autonomous mine concept. So it's interesting to think about how does the transition to automation and construction compare to all of these other fields? And I'd argue it's somewhere in the middle. The hype curve is useful. You can think about it in terms of autonomous vehicles. You can't really deploy anything but nearly perfect autonomous vehicles. But in construction robotics, you might be able to argue that you can have various milestones along the capability curve. And there's 2 key ones I put there. One is one where you have vigilant human operators supervising these technologies constantly, which is a very tough ask of humans, as we've seen in autonomous vehicles. The second viable threshold, you could argue, could be highly autonomous robots that know when they're failing, still throw over control to a human, but it doesn't require constant vigilance by the human operator. And that's a critical threshold there. All right, I think I stuck to time reasonably well. Thank you again to the organizers, and I look forward to the rest of the day. Thank you.